My name is Kaleb and Naveed, and I'm sharing my work from the Robotics Institute Summer Scholars Program 2021 on informative and fast exploration planning using UAV for reconnaissance operations. First, I would like to share about the motivation behind this work. Data acquisition and fast exploration, the search space is very essential to the search and rescue operations. It is very important to search the whole space as fast as possible to ensure the minimum time response. But at the same time, it is very important to pause exploration and focus on the object to gain more information about it. Thus, the main dilemma is to maintain a balance between fast exploration and data acquisition. Existing work focuses on optimizing either data acquisition or fast exploration. This gives non-optimal solutions. Thus, in this work, our goal is to develop a framework that ensures and prioritizes information gain while maintaining fast exploration. Working towards our goal, we propose prioritized fuel, which is built on top of fuel algorithm, fast UAV exploration proposed by Voyage2 et al. The high level of the structure contains two high-level planner choices, which are exploration planning for faster coverage and informative planning for data acquisition. The second level uses Frontier Information Structure (FIS) and Frontier Priority Queue (FPQ) to store information about frontier clusters. FIS was originally introduced by fuel algorithm, but we modify this according to our requirements. Also on second level, we introduce FPQ, which is exclusive to high-level informative planner. The low-level planner uses three-step planner. For Frontier Information Structure, we add two modifications to the original FIS in the fuel paper. FIS contains information about frontier cells that belong to the cluster, average position of the cluster, bounding box of the cluster, bounding box of the object of interest, which is our first modification, probability of the detected object, which is our second modification, viewpoints around the cluster, and connection costs to the other clusters. For example, let's see this picture. In this picture, the ships are detected and the bounding boxes are drawn around them. We store the information about the bounding box and probability of the confidence of protection in FIS. Moreover, we introduced Frontier Priority Queue to store information about the high-priority frontiers. High-priority frontier clusters are clusters whose bounding boxes overlaps with the object of interest bounding box. For more clarification, let's see this example. Let's assume we have a drone flying over sea, and the red region is drone's field of view. As the UAV flies over the sea, it detects the object of interest, and as shown here, the bounding box of the object of interest overlaps with the bounding box of the cluster, shown in black. Now this frontier cluster is considered as high priority cluster and its information is stored in the FPQ. Let's see different cases of FPQ. In case 1, let's suppose that FPQ contains at least one frontier. This means that exploration planning is paused and informative planner is used to generate minimum time trajectories to explore high priority frontiers using three-step planner. For case 2, if FPQ contains no frontier, using exploration planner, all frontiers are considered equal and minimum time trajectories are generated among any active frontiers using three-step planner. Three-step planner is taken from the fuel algorithm. The three steps include global path planning, local viewpoint refinement, and minimum time B-spline trajectory generation. A global path planner creates a global path from the current cluster to all active frontier clusters by posing problem as asymmetric traveling salesman's problem. First, it calculates the connection cost between the two clusters using the time lower bound equation, and then it calculates DSP using the equation shown below. In the second step, instead of moving to the average position of the cluster, local viewpoint refinement procedure chooses point, XYZ, and yaw angle, which maximizes sensor coverage. In the third step, minimum time B-spline continuous trajectories are generated by optimizing all parameters of the B-splines. This routine produces flat outputs as quad rotor dynamics are flat. We run our experiments in the light UAV simulator. Table 2 shows the results of the 10 experiments we conducted. We mainly compared our approach against fuel algorithm. We used two metrics, data acquisition time and total exploration time. Data acquisition time means the time spent on exploring or covering high priority frontiers in FPQ once object of interest is detected. Meanwhile, total exploration time refers to the total time spent exploring the whole search region. The table shows that the average value of data acquisition time decreased by almost 2 times as compared to fuel algorithm, which resulted in faster data acquisition in our approach. Here the video of the UAV exploring the search region, twice the original speed, is shown. The rectangular objects are obstacles and circles are assigned as objects of interest. The UAV can be seen focusing on circles once they're detected. To summarize, in this work we propose prioritized fuel, which is a hierarchical structure to maintain a balance between exploration planning for faster coverage and informative planning for data acquisition. The results show that the prioritized fuel decreased the overall time to explore frontiers near object of interest by almost 30 to 40% in the simulation environment. Thank you for listening.